Hi there and welcome back. So in the previous videos, we started talking about integrals of complex functions along a curve C, and in particular in the last video, we saw that let's say we have some curve C, and we are integrating the complex function WZ, let's say with real part U and imaginary part V. Then the integral of the function along the curve C can be thought of as the work done by a dual field, by a field which is dual to the complex function W. In other words, we first define the conjugate of this complex function, which is U minus IV, and then consider a vector which has the x component U and y component minus V. And then the work done by this dual field constitutes the real part of this integral, WZ dV, plus the flux of the dual vector field constitutes the imaginary part of the integral. So for instance, this is the curve. Then we define a direction tangent. Let's say we have an infinitesimal segment ds. We have a direction which is tangent to the curve, denoted by the vector t, and then we have a direction which is normal to the curve at that point, denoted by the unit vector n. Then we consider a dual field E tilde and calculate the flux or the flow of this field through this curve and the work done by this field along this curve. Now, one of the things we did not emphasize too much in the last video, which is if you look at the flux done, flux transported by this vector field along the curve C, or an infinitesimal segment of this curve, then the flux is computed by taking the projection of this vector field along the normal to the curve multiplied by the length of the segment that we are considering. And this is the infinitesimal flux, and when we integrate this, we get the total flux. Now, the way we've defined it, or this quantity, has both a magnitude and a direction. In other words, if for instance the vector field E tilde is indeed in the way we've drawn here, then its projection along the normal is positive, and then E dot n will be a positive quantity. We always assume that the length of the segment is positive, so then this will be positive, and this means that there is a flux which is going, if the normal to the curve is denoted by this direction, then there's a flux which is going outward from the curve. Like if something is flowing this, then it's flowing outwards in this direction. However, if for instance the vector field was pointing in this direction, then we see that the projection of this vector field along the normal would be negative, and in that case we'll say that there's a flux going in this direction, or if you want to think of this as some region like this, then we can say that there is flux flowing into the region, and in case it's positive, then we'll say that there is flux flow out of the region. In the same way, the work done, the infinitesimal work done, has both a magnitude and a direction, and the total work done likewise. So the infinitesimal work done is E dot the tangent times ds. And again, depending upon the orientation of E with respect to the tangent vector, this quantity can be either positive or negative, and likewise the work done could be positive or negative. So for instance, if the vector field was pointing in this direction and the tangent is still in this direction, then its projection along the tangent will be negative, and in that case the work done will be negative. So that's an important point to emphasize, that flux and work done have both magnitude and direction associated with it. And this becomes important, especially when we extend our discussion from an open curve C to a closed curve C, or a region of space that's enclosed within some simple loop. We're just considering simple loop for now, and we'll talk about loops. What does a simple loop mean really in some of the future videos. But for now, a simple loop, we can just imagine just one loop of some arbitrary shape drawn through a region of space, and there's an arrow, so we have associated a sense with it that if we are moving along this loop, then we are propagating in the counterclockwise direction. So in such a closed region of space, we can also talk about flux and work done, flux through this region of space, and the work done along the loop, and the work done that's done along this closed loop, just like we were talking about work done and flux along some open curve C. We can also talk about these ideas when we consider a closed loop. And in this case, the integrals, for instance, are denoted with a circle along the integral, and you typically draw an arrow indicating how you are traversing the curve, the closed curve C, in which direction are you traversing the curve. So if it's counterclockwise, you'll draw an arrow in the counterclockwise sense. If it's clockwise, you'll draw an arrow in this in this sense, and denote, and you have a small symbol C which labels the particular curve that you're traversing. So let's just spend a little bit of time about this, discussing these closed loops or regions of space where we've drawn a closed loop. And again, if you now think of some simple vector field, for instance, let's just consider a uniform field which is going like this. Okay. So this is some kind of a uniform field that we've drawn. And one thing you notice is that whatever is the flux coming in, so we've drawn 4 lines coming in, there are 4 lines going out roughly. So whatever is the flux coming in will be the flux going out. So if you just imagine fluid flowing from this end of the board right across this region of space, then all the fluid, if there's nothing inside this region which sort of either absorbs that fluid or adds to that fluid, then whatever comes in will go out. And so sort of these kinds of ideas brings us to defining sort of a couple of or sort of characterizing flows or vector fields in at least 2 different ways, and that's what we just want to sort of quickly discuss now, which is one of the definitions is that of a sourceless field. And we just think of this as a definition. So we just say that a field through a region of space is sourceless if through any closed curve, any closed loop or any closed curve drawn through that region of space, the net flux through that closed loop is 0. So a field is sourceless if net flux through any loop, any closed curve, and we're just talking about simple curves, so I just write simple curves for now. Any simple curve. So if net flux through any closed curve in that region of space is 0. And we just define such a field as being a sourceless field. So why is it called sourceless? Well, again, let's just consider this loop. So again, these ideas are borrowed from our sort of intuition with how fluids behave, but you could also apply them to charges and any other kind of field. So let's just think of a fluid, for instance. If there is a source of fluid here, imagine some kind of a fountain head or a tap that's located here, then what will happen is that there might be a flow which is radially flowing out of that region, and in this case there will be a net flux through any loop and through any closed loop which we draw around the source. And if you recall, we discussed an idea related to this in one of the earlier videos, but we did not quantify, we did not actually calculate the flux in the way that we're sort of thinking about now. But although we did discuss in terms of how many units of fluid is crossing sort of this kind of a loop. So I'll just put a link to that video. But so if you have some kind of a source located here, and that could be a source of a fluid or source of charge, then through a closed loop drawn around that source, there will be a net flux. And this sort of motivates our definition of a sourceless region, which is where if instead of drawing a loop around the source, we draw a loop somewhere else in the region of space like this, then whatever is the flux or fluid flowing through this curve, whatever is the flux of the fluid or the fluid that enters this curve is equal to the flux that will be flowing out of the curve, because there is nothing that is either absorbing the fluid or nothing that's adding to the fluid. So that such a region we'll call sourceless region, or the field in this case we'll just say that it's a sourceless field in this region of space. So one way to write this is that if the flux through a closed loop, through any closed loop, through a region of space, the net flux is 0, then we say that the field in that region is sourceless or that region is sourceless. And the same way, we have the notion of a conservative field or an irrotational field, conservative or irrotational. And this happens when the work done along a closed curve C by the field is 0. So the same idea, but now this time we are evaluating the work done along a closed loop, and if that is 0, then we define that region of space or that field in that region of space as conservative or irrotational. So these two ideas sort of we will see that sort of first of all they bring in the idea of talking about closed loops in region of space or closed curves in region of space, and by sort of carrying forward this discussion of how do we evaluate the flux and the work done or circulation through such a closed loop, we'll see that we'll be able to derive relationships between an integral formulation of flux and work done, a relation between an integral formulation and their local or differential formulations, and these in turn will help further our understanding of complex integrals in ways that we'll see in future videos. So we have been talking about a few different ideas, but hopefully they'll soon tie up together to sort of and sort of help us understand complex integrals better. So hope this is of some use, and we'll surely carry on this discussion forward, and hope to see you soon. Thanks for watching.